Okay, in this video, we're going to look at problems involving relative velocity. That means the velocity as measured relative to a different coordinate system. So far, we've described all of our kinematics quantities, that'd be things like position, velocity, acceleration, and so forth, in terms of stationary reference frames. That is, I've got me an XYZ coordinate system, or even just an XY coordinate system, XY, and it's fixed on the ground, and so I've got my coordinate system and I can measure the position of something, I can measure its velocity, etc. Now what we want to do is we want to say what happens if the coordinate system isn't fixed but is moving itself. And for now we're just going to consider motion where the coordinate system is moving at a constant velocity. We'll look at what happens when it accelerates later on. So the simplest example of this is a ball that is thrown off of a train that is moving. And so here I have, as an example, this ball, and this person is on top of this moving train car. The train is moving with some velocity, and the ball is thrown off the train. And the question is, how would you measure the velocity of the ball? And the answer is, it depends. Because you could measure it from a coordinate system that's fixed to the train. In other words, this green coordinate system here is glued onto the train. It's moving with the train. And so you could measure the velocity, and that would be if this guy who threw the ball had a radar gun, he would measure the velocity to be a certain amount. But someone on the ground who would be measuring from a coordinate system that would be fixed to the ground, say this purple XY coordinate system here, he would measure a different velocity from the ball, because when this guy threw the ball, it was already moving with the velocity of the train, and then it would get the extra velocity that the ball was thrown with. And so this guy would measure a different velocity than this guy would. And what's different is the reference frame that they would be using. This guy would be using the green coordinate system, and this guy would be using the purple coordinate system. And there's a relationship between those velocities, and it's written down in this equation below. And I just want to go over what the notation of this equation means. And so here I have v b slash g. That means the velocity of the ball relative to the ground. The slash means relative to. So the velocity of the ball relative to the ground means the velocity of the ball measured from this purple coordinate system that is fixed on the ground. That would be equal to the velocity of the ball relative to the train. Remember, the slash means relative, so this is the velocity of the ball relative to the train. In other words, the velocity of the ball is measured from this green coordinate system that's glued onto the train and moving with the train, plus the velocity of the train as measured from the ground. So that would be the velocity of the train relative to the ground. So again, the whole thing, the velocity of the ball relative to the ground over here is equal to the velocity of the ball relative to the train plus the velocity of the train relative to the ground. Okay, so here we have a problem. A person on a train with a velocity of 40 miles per hour relative to the ground throws a baseball with a velocity of 60 miles per hour relative to the train in the same direction as the train's motion. What is the velocity relative to the ground? And that would be the velocity of the ball relative to the ground. And what if it's thrown in the other way? What if it's thrown opposite to the motion? So this is the question, and we have our working equation that we talked about in the previous slide. We know that the velocity of the ball, which is what we're looking for, is simply going to be the velocity of the ball relative to the train, that's relative to this green coordinate system here, plus the velocity of the train relative to the ground. Okay, so we have this equation that we saw in the previous screen. This is the velocity of the ball relative to the ground, is the velocity of the ball relative to the train, plus the velocity of the train relative to the ground. I've got my little picture here that I've sketched in. So here I have the train coordinate system, here I have the ground coordinate system, and here's the little ball. We're given in the problem that the velocity of the ball with respect to the train was 40 miles per hour, and the velocity of the train with respect to the ground was 60 miles per hour. And we can see from the picture that both are moving in the x direction. The x direction of both coordinate systems are lined up. So both of these guys are going in the x direction. And so we can say that the velocity is 40 miles per hour in the x-hat direction plus 60 miles per hour in the x-hat direction again. And so we can simply add together those velocities. And so the velocity of the ball relative to the ground is going to be 100 miles per hour. That is the velocity that it was thrown with, the 40 miles per hour, plus the velocity of the train, which is 60 miles per hour. Now, if the ball is thrown in the opposite direction, so instead of being thrown with the motion of the train is going this way. If the ball were instead thrown in the opposite direction, then we would have it being thrown in the negative x-hat direction. Here would be my x-axis here, and I would have the same for the green one. So here we would say that the velocity of the ball with respect to the ground would be 40 miles per hour in the negative x-hat direction, plus the 60 miles per hour that the train was moving, and then the ball, even though it was thrown backwards, it would actually have a forward motion of 20 miles per hour. How do I know it's forward? Because the coefficient here is positive. This 20 miles per hour is positive. That means to the right. It's in the positive x-hat direction. So even though this ball was thrown backwards, someone on the ground would still measure it as moving forward. Isn't that crazy? But that's just the way that it works. And hopefully that does make sense. Now, one thing that does make this problem simpler is that all the motions were along one direction of motion, along the x-hat or the negative x-hat. But of course, these things are all vectors. We see the little arrows on top of these equations. That means that they can have directions that are not in line with one another, and then the addition gets more complicated. But analyzing these kinds of problems doesn't have to be any more complicated than this. So I want to show you here a general approach for working more complicated relative velocity problems. The main difficulty is always setting these problems up. My students in the past, they really struggle with setting the problems up because once you have the picture drawn, once you understand what's going on in the picture, the actual math in solving these problems is quite straightforward. It's just basic algebra and trigonometry. But setting up the picture correctly, that can be a challenge. And so one of the things I'd like you to think about is how to use an analogy, because you can take the most complicated relative velocity problems and basically imagine them as being similar to that basic example of a ball being thrown off of a train that we just looked at. All you have to do is, in whatever problem you're being asked, figure out what of those things moving corresponds to the ball and which one corresponds to the train. And then you want to figure out what's like the ground. And the one that's like the ground is going to be obvious. And, they may call it the shore, or they may call it the earth, or they may call it some other word, but it's going to be pretty clear that it's the ground that they're talking about. So really, what it's going to come down to is what's like the ball and what's like the train. And once you figure out this analogy, you can write down an equation to show you how to draw the picture. And I think that'll make sense when we do a few examples. So here's an example. A motorboat has a speed in still water of 10 meters per second, and it's crossing a wide river with a strong current that's moving 7 meters per second, as shown in the picture below. So here is the boat, and he is going straight across the river, and the river itself is moving to the right. Now, if the bow of the boat is kept directly aimed across the river, what's going to be its relative velocity to an observer standing on the shore? So, here we have a coordinate system that is fixed on the ground, and I could label that one as S for shore. So we can talk about the velocity of the boat relative to the shore, but we can also talk about the velocity of the boat relative to the river. And so I'm going to draw a little coordinate system on the river here, and this is the velocity of the boat relative to the river. Now, here's the thing, because that can be a little bit confusing. What does that mean, the velocity of the boat relative to the river? That means the velocity of the boat relative to a coordinate system that's moving as the river moves. So imagine a little bitty piece of water, a little bitty volume of water that's flowing down the river this way. So this whole coordinate system is flowing to the right. Now, that's the river that's dragging the boat with it. So the boat is aimed directly across the river, and so it's going to be dragged to the right, but this R coordinate system, the one in green, is going to be dragged at the right at the same rate. So what that means is that the velocity of the boat measured from the river is going to go straight across the river. It's going to seem to be going straight because in reality, relative to the ground, they're both moving to the right. But because the water is moving to the right and the boat are moving to the right in tandem, the boat measured from here will be seen as going straight across. Now, of course, someone on the shore would see the boat going forward and to the side at the same time, so they would see the boat going off diagonally. And that is basically what's going to happen. So measured relative to the river, the boat's going to seem to be going straight across. Measured relative to the shore, the boat's going to be seen as going off at an angle. Now, on the previous slide, I talked about using an analogy to the ball thrown off the train problem in order to help you draw the picture. It's probably pretty obvious to many of you how to draw the picture without needing to resort to that analogy. That's fine. You don't have to use the analogy for every problem. It's just a tool that I'm making available to you so that if you get a problem where it's difficult to draw the picture, you don't see immediately how the picture should be drawn, you can use this analogy tool to help you draw the picture. If you don't need it, if it's obvious which way the vectors are going, just draw the picture. I'm perfectly fine with that. But I'm going to show you how to apply that analogy to this simple problem, even though most of you probably wouldn't need me to, just so that you can see the process of applying that analogy. So let's look back at our original problem. We have the ground and the train and the ball thrown off the train. And so what are we going to do with this? So we talked about previously that we can write down an equation, the velocity of the ball relative to the ground, that's relative to the purple coordinate system here, is equal to the velocity of the ball relative to the train, that's this green coordinate system that's moving with the train, and that's a key thing, it's moving with the train, then that's going to be plus the velocity of the train relative to the ground. And so we talked about what all that means. We want to solve this problem, which looks completely different. You know, we have things going at right angles to each other now. We have the shore and the boat and the river. And so we want to draw the right picture. How do we do that? Well, we can use this train problem as our guide because I think any of you could write down this equation. If you think about it, what's the velocity of the ball relative to the ground? If you can suss out that it's the velocity relative to the train plus the velocity of the train relative to the ground, you can write down this equation and that will be a guide for any other relative velocity problem you might need to work. All you have to do is figure out what corresponds to the ball, what corresponds to the train, and what corresponds to the ground. Now I think it's pretty obvious that the shore is what corresponds to the ground, and so anywhere I have a G here, I can put an S in my equation. And this is going to help me figure out what the equivalent vector equation is to my problem. Now, the question is, which one's like the ball and which one's like the train? And I'm going to assert that the boat is like the ball and the river is like the train. Remember we talked about that the coordinate system that goes with the river is moving with the river. And so if I draw a coordinate system that is moving with the river, that's going to be similar to this coordinate system up above, which is moving with the train. And so that suggests that the river is like the train. And that leaves the boat, which has to be like the ball. And so anywhere I have a B for ball, I'm going to leave it B for boat. Anywhere I have a T for train, I'm going to replace it with an R. Anywhere I have a G, I'm going to replace it with an S for shore. And so this equation up above, when you make those changes, becomes the velocity of the boat relative to the shore equals the velocity of the boat relative to the river plus the velocity of the river relative to the shore. And this equation tells you how to draw the picture. This is just a vector sum, and we know how to draw vector sums. We do tail to tip twice. So here's the equation. We've got the velocity of the ball relative to the shore, and that's what we're looking for, is the velocity of the ball relative to the river. And so we were told that that is going straight across the river like this, plus the velocity of the river with respect to the shore. And we were told that that one goes to the right because the river was flowing to the right. And so this tail to tip twice, this is my vector sum, and this gives me the means of drawing the picture. Now, once you have drawn the picture with the vectors, what you have is a triangle. And you can use your trig, and you can use your Pythagorean theorem, and all the tools you know for handling triangles. And so we can simply say that what we're looking for is the magnitude here of the velocity of the ball with respect to the shore, and it's going to be this side squared plus that side squared is equal to that side squared, just the Pythagorean theorem. And so if I plug in the numbers, I end up with the magnitude of the speed, the magnitude of the velocity, the speed, is going to be 12.2 meters per second. And then, if I want the angle, I can simply use the arctangent, because I know this is the opposite, this is the adjacent, and when you plug those numbers in, you get 34 degrees. Now, if we look at this angle here, we can see that it's going from the north axis towards the east axis. That's the direction the angle is going. And so that angle would be east of north. And so we can say that the velocity relative to the shore is 12.2 meters per second at an angle of 34 degrees east of north. And it's that easy to do. Now, as I said, this business of doing the analogy, you might have been able to just see this picture from the original problem. And if you can draw the picture, if you understand what the parts mean and you can put it together, then do that. Don't use the analogy if you don't need it, then it's just busy work. It's when you get confused, that's when you want to use the analogy to help you draw the picture. Now, let's look at a more challenging problem. A plane has an airspeed, that is the velocity in still air, or the velocity with respect to the air, of 200 kilometers per hour. The pilot wants to fly due north, but encounters an eastward wind of 50 kilometers per hour. That's a wind pointing towards the east. To maintain a northward trajectory, at what angle must the pilot's heading be? That's part A. And then part B says, what will the pilot's ground speed, that is the velocity relative to the ground, be? Okay, the first thing we want to do is we want to look at what we're given in the problem. So we know that the magnitude of the airspeed is 200 kilometers per hour, and we know that the wind is eastward at 50 kilometers per hour, and we know that the direction we want to go is northward. And so this problem is a little weird because we've got some vectors we know the magnitude but not the direction, and other vectors we know the direction but not the magnitude. And of course the air, we know both its magnitude and direction, but we're going to have to draw the right picture, and it gets confusing because we don't have all the information all at once like we did in the last problem. So let's look at what we do have. We know that the velocity of the plane relative to the ground is going to go due north. That's what we're told. We want to maintain a northward trajectory relative to the ground. And we know that the velocity of the air with respect to the ground, that's the wind, the velocity of the air with respect to the ground is going to the east, and we know that it's 50 kilometers per hour. Now, we do not know what the magnitude of this vector is, but we do know that the magnitude of the velocity with respect to the air, the plane with respect to the air, is going to be 200 kilometers per hour. We just don't know what direction it's in yet. But what we need to do is we need to draw the picture, because when we can draw the picture, we can find the unknown magnitude. It's just going to be an unknown side of a triangle, and we can use the Pythagorean theorem. Or we can also find the direction, because we know this guy's 200 kilometers per hour, but we don't know what angle it's going at. And so that's the other thing that we're trying to find in the problem. We want to know what's part A says, what's the angle to turn this guy so that you'll end up with this guy going due north, and then how fast will this be going relative to the ground? So again, that can be confusing, but if we use our analogy, I think it's pretty clear. The ground is going to be like the ground. The air, or the wind, is going to be like the train, because that's when we say the velocity relative to the air or relative to the wind, that's one where the coordinate system is going to be moving along with the air, just like the coordinate system was moving along with the train. So it's pretty clear, hopefully, that that's going to be the one that's like the train. And then the velocity of the plane is the one that's going to be like the ball. And so everywhere I have a B up here, I'll replace it with a P. Everywhere I have a T for train, I'm going to replace it with A for air. And then the G is going to be the same because the ground is the ground. And so when I make those substitutions, this is the equation I get. Vp/g, that's the velocity of the plane relative to the ground, equals the velocity of the plane relative to the air, plus the velocity of the air relative to the ground. And that tells me how to draw the picture. /a. So here's what we know on the left, and here's the equation on the right that we want to use as a guide to tell us how to draw the picture. Now, we know this is what our vector sum is going to be equal to. So we want this thing, which is going straight up towards the north, is got to be equal to this guy plus that guy. And so I'm going to scoot this guy over here and redraw it. So I've got my Vp/g. Now, how do we do a vector sum? So the first term in the sum is this Vp/a here. We know this guy's what we're going to end up with, and so we're going to start at the tail of this guy, and whatever way this guy goes, we know it's going to start here and it's going to go to some ending point, and then where it ends, the second vector is going to start, and it's going to end up with its arrowhead pointing right there. And so what I can do is I can take this arrow, this Va/g, and I can draw it in because I know that it's got to end up right there. And so this is my Va/g. And then what am I left with? Well, I'm going to have the Vp/a. That's the one I don't know. But I know it's got to start here and it's got to end there. So I can just draw that in. And that's what the vector must look like for Vp/a. And so now we have a right triangle, and we can apply all the things we know about right triangles. But really, all we've done is we've used this equation as a guide to tell us how to order the vectors and draw the triangle. So once we have the triangle, it's very simple to solve the rest of the problem. Okay, so here is the equation that we ended up with. And we have this triangle here, and what we want is we know that VAG, that's 50, so this is 50. And we know that VPA, this is this purple one here, we know that that's 200. And so we can use the Pythagorean theorem to find this unknown side. And so just applying, so forget the vectors for a minute and think of this just as lengths of sides of triangles. We know that this squared, that's the hypotenuse squared, is equal to that squared plus that squared, that's the squares of the other two sides. And we want to solve for this guy right here, VPG. We want to know how long that guy is. And so if I bring this guy over here, it becomes negative. Then I take the square root of both sides, and I get VPG is the square root of VPA squared minus VAG squared. I plug in the numbers, and at that point the problem is solved. I get that the velocity of the plane relative to the ground is 193 kilometers per hour. Now the angle we can get by using the arc sign, because we know we're given explicitly that this side is 200 and this side is 50, and so we can do the opposite over the hypotenuse, gives us 50 over 200, take the arc sign, and we end up with 14.5 degrees. And from our little legend here, we know that the angle theta is going to the west from the north axis, so that would be 14.5 degrees west of north. So that we don't get completely bogged down in the math, what all does this mean exactly? So the pilot has a plane that can go 200 kilometers per hour, and he wants to fly it due north. But because there's a wind, he can't point his plane due north. If he tried to point the plane due north, it would go off at an angle like the boat did in the previous problem. So in order to keep it from going off at an angle, he has to point it into the wind. And so how much does he have to point it into the wind? That's the angle that we figured out. And then we know it's going 200 kilometers per hour this way in the direction where he's turned it into the wind. So how fast would he be going on the straight path? In other words, someone on the ground looking at that plane would see that plane flying due north overhead. They would look up and they would see it going due north overhead, and they would measure that speed of that plane not as 200, but because it's fighting against the wind, it would actually be going 193. And that's what we figured out. How fast the plane is going relative to someone standing on the ground looking up, and, you know, what direction the pilot would have to turn the plane into the wind so that it would go due north as the pilot intends. Now, this is a problem that I really like because if you understand how to work these problems, it's really easy. But if you don't really strongly understand how to draw these pictures, this problem can be very challenging. But if you use this train analogy, you'll find that this problem is among the easiest problems to work that there is. But if you don't use the train analogy, I find that my students really used to struggle with it before I taught them how to approach it by thinking about that darn train. So let's look at what we have. Two cars are traveling at a right angle around a corner as shown. So this car is going to the right, this car is going up, and both of these are velocities measured relative to the Earth. And so there's some coordinate system that is on the Earth, and of course that's going to be like the ground, but this is the coordinate system relative to the Earth, and so I've got my X and my Y here, and so I'm measuring both of these velocities relative to this fixed coordinate system that's on the Earth or on the ground, and they're both going 40 kilometers per hour. They're just going in different directions. And so the question is, what would the velocity of car 1 be with respect to car 2? And really what that means is relative to a coordinate system that's moving to the right, glued to car 2, moving along with car 2. And so what relative to the ground, this is 40 kilometers per hour, but relative to this coordinate system that's moving over to the right, how would you draw that picture? I can tell you it's not obvious to most people. It's really a tricky problem. And this is actually a problem that came from the textbook by Giancoli, which is a really good textbook and it has some really clever problems in it. But this problem is one that I really like, and so I always show this one to my class. So let's go back to that equation, and hopefully you can write this equation down by yourself now. The velocity of the ball relative to the ground, the velocity of the ball relative to the ground, equals the velocity of the ball relative to the train, plus the velocity of the train relative to the ground. And what we want is we want to figure out what is like the ball, what's like the ground, and what's like the train. Now, as I said, obviously the Earth is like the ground, and so wherever there's a G here, I'm going to replace that with an E. And we have the velocity of 1 with respect to the Earth and the velocity of 2 with respect to the Earth. What we want is the velocity of car 1 with respect to car 2. And so that tells us, if we look up here, the 1/2 would be like this term, because this is the Earth and this is the Earth, and so this would be like 1/2. We want the velocity measured to this coordinate system that's moving like the coordinate system on the train is moving, and so that tells us that car 2 is like the train. That means that car 1 has to be like the ball, and that tells us how to write down the equation. The velocity of car 1 with respect to the Earth is the velocity of car 1 with respect to 2, plus the velocity of car 2 with respect to the Earth. And so that's the equation that tells us how to draw the picture. And keep in mind, we know this V1/E is pointing up, and this V2/E is pointing to the right. So now we just need to do the tail to tip thing, add these as a vector, and that'll tell us how to draw the picture. So what we've got V1/E is equal to V1/2 plus V2/E. That's the equation we just came up with. And what we want to find is this guy. We want to solve for him. So I can take this term, move it over here. It's going to become negative on the other side. But if I solve for V1/2, that's the velocity of car 1 with respect to car 2. That's going to be v1 slash e minus v2 slash e. And now I can draw the picture for this. And we know how to do a vector subtraction, how to draw a vector subtraction. So one way that's easy is I can take that v2 slash e, this vector here, and I can flip it 180 degrees, and that becomes negative v2 slash e. And then I can just add that to v1 slash e, and that's the picture. So here I have my v1 slash e, which is pointing up, my negative v2 slash e, which is flipped around 180 degrees, and then the equation tells us that this plus this is going to be my v1 slash 2, and so I can draw the picture. Now, because both of these are the same value, I think you can tell automatically that this is going to be a 45-degree angle. And so that's going to be a 45-degree angle, but if you didn't know that, you just use your trig. You just use your basic trig to figure out what the angle is, and then you can use the Pythagorean theorem to get the speed of v1 slash 2. And so again, this is what we have. This is the picture. This is the equation that we use to draw the picture. But once you've drawn the picture, forget about the vectors. You just have a triangle. And so you know Pythagorean theorem. The Pythagorean theorem gives us that v1 slash 2 is going to be that squared plus that squared square root. Plug in the numbers and you get the answer, easy peasy. And so that's the easy way to work these problems. Now, there is a caveat, and you're going to get to do a homework problem with this. You don't always end up with a right triangle. And so sometimes you might end up with a triangle that looks like this, something like that. And so how do you draw that? And so you might have this vector here and this vector there. They add together to give you this vector. Well, you just add them like vectors. If it comes down to that, if you don't have a right triangle, you can break vectors down, draw a coordinate system, draw an xy coordinate system, something like this. And then you can break all of these vectors into xy coordinates, xy components, and then do just regular vector addition. And that'll give you a solution. And so that's all you have to do. The worst of these problems, you're going to end up with just a triangle. And so you do all the stuff you know about triangles, and that makes solving the problems easy. So you're going to get some homework on this to kind of practice this. And again, this analogy, I don't care if you use this analogy or not, but I wanted to show it to you because on these complicated and confusing problems like this one, it can really make them a lot easier. So I suggest you practice with it, even if you don't need it, just so that you get it down how to use it. But once you've got it sorted out and it's clear how to use it, just use it when you need it. And that is my advice.